Continuing our discussion of harmonic motion, we're now going to start talking about pendulums. And today's example problem is a classic pendulum. We're going to be talking about a grandfather clock. So our grandfather clock, we are going to initially assume is a point mass of 2 kilograms. So we've got 2 kilograms acting at the end of a unknown length. We can set the length ourselves, so that's what we're going to be doing here in a second. An unknown length of string that has no mass to it. And that length of string is going to be defined in order to make sure that the period of our pendulum, so the time that it takes to swing all the way across and then all the way back, is 2 seconds. We want a full cycle to be across in 2 seconds, back in 2 seconds. And that is, that's the basis of the problem. So there are a bunch of things that I'm asking for this. We're going to figure out the length and the overall movement of our pendulum. We're then going to start talking about where our pendulum is after a certain amount of time, and then we're finally going to say, okay, well, what happens if our pendulum, instead of being a single massless string, is some rod with some given length? How does that affect our length of our overall rod? And with that, there's just a lot to write down for our what defines, so I'm going to kind of take it one step at a time. So our first step, we're just going to be looking at this overall pendulum here, and we're going to figure out what length that needs to be. So our what defines for this first piece here, what we want is we want to figure out what that length is in order to get our oscillation set up perfectly. And sorry, we're slightly off the board there. So our what defines, we want to figure out our length, and we want to figure out our maximum width, or actually really our minimum width. So as our pendulum swings, it's going to go from one side all the way over to the other. And we are told that we want this swing to start at 10 degrees, meaning that it's going to end at 10 degrees. And that is going to result in some distance here. So this is our width. And that width is going to define how big we have to make our cabinet in order to make all of this work. So we want to know what width our cabinet for our grandfather clock needs to be if we want a 10-degree swing on the grandfather clock. Okay. With that, let's go ahead and get started. What we know that we want a period of 2 seconds. And so I'm going to go ahead and write that down. Period is 2 seconds, and that is 2 seconds per full cycle of our pendulum. 2 seconds to go all the way across and all the way back. Now, just like with springs and just like with rotation, we're going to be working with omega in order to make things work. So we need to change this into a omega. So in this case, our omega is a rotational rate, or a rate that we're moving through this entire piece. It's not a full rotational rate. We're actually going to be finding rotational rate as we go here. But it is going to help us define our overall system. So our omega pendulum is what we want. And our omega pendulum is going to be in radians per second. So we need to change our period into radians per second. So in order to do this, we're first going to have to flip it over. So our frequency is going to be equal to 1 over our period, frequency being in cycles per second. So we have frequency is 1 over 2 seconds per cycle. That is going to be 0.5 cycles per second. And then we can just do our normal 0.5 cycles per second. And a cycle, a full cycle, is going through 2 pi radians, and that is going to give me a omega value of pi, yeah, it's just pi radians per second. Although this is my omega of the pendulum. This is not a constant rate that I'm rotating at. So be careful, we got 2 omegas going on in these equations. That can easily be screwed up. So we have been given some information about this omega pendulum. We've been told that the omega of the pendulum for a point mass system only, we're going to get to the equation for a non-point mass system only, is going to be the square root of our gravitational constant divided by the length. So in this case, we want to know our length. So our length is going to be equal to our gravity divided by our omega for the pendulum squared. So that is going to be equal to 9.81 meters per second squared divided by pi radians per second, that whole thing squared. And that is going to give me a length for my pendulum of 0.994 meters. And that is what this length needs to be in order to satisfy 994 meters, in order to have a period of 2 seconds. So that's the first piece done. Now, given that length, we need to figure out what we want our overall width of our cabinet to be. And that is just a question of our overall size. That's just a trigonometry question that we have to go through here. So with that, if I go ahead and draw this out again, I have a length of 0.994 meters, and I have my overall length here that I need, and I know that each of these guys is 10 degrees. So this length here is half of my width, but this is a 90-degree angle, so half of the width is going to be equal to, so the sine of 10 degrees is half of the width divided by 0.994 meters, so it's going to be 0.994 meters times the sine of 10 degrees. And I'm going to have to, in order to get my whole width, I'm going to have to use this side as well. So I'm going to have to just multiply both sides by 2. So I've got 0.994 times sine of 10 times 2, which is going to give me a total width of 0.345 meters. And that is the first section of our calculation. So going back to our question here, next thing we are asked is we are asked for a bunch of things, and we'll want to know what is happening more or less with our pendulum at a time of 0.7 seconds. So we're going to guess that it's about here. So time equals 0.7 seconds. Hopefully I wrote that one down right. Yep, so we want to know what's happening at 0.7 seconds. And what do I want to know? I want to know, we'll call this, we'll just call it at 0.7 seconds. I want to know my angle at 0.7 seconds. I would like to know my angular velocity at 0.7 seconds. I would like to know my angular acceleration as 0.7 seconds. And then I would like to know the velocity. Do I want the position? I do want the position. I want the position in the x at 0.7 seconds. I want the velocity in the x at 0.7 seconds. And I am out of space, so I want my acceleration in the x at 0.7 seconds. And I need to find all of those things. Well, luckily we have an equation for this. And one thing that I probably should have held on to is that omega, because we're going to need that. Omega pendulum is going to be equal to pi radians per second. That was something that we just erased. It was over here a second ago. Note that this omega p is not going to be this omega right here. This omega p talks about how quickly we're going through this cycle. This omega p talks about the angular velocity of our piece at any different point in our cycle, which very clearly is changing because as we go left to right, we're going in the positive direction. As we go right to left, we're going in the negative direction. Can't be the same number. And speaking of which, I am going to go ahead and mark that I'm going to call everything to the right the positive direction. Everything rotating this way, I'm going to be calling the positive direction of rotation. Okay, so let's do this. We have been given the equation that theta at any given time is going to be equal to our amplitude of theta, so our maximum angle, times the cosine, I believe. Don't want to write something down. Yeah, cosine of omega t plus phi, and we can have a plus theta naught here. We can have a plus an x naught if we want an offset in our other. And basically this is if it's not calling 0 degrees straight down, and the x naught, if we were going back to our springs, would be if we're not calling our 0 displacement x 0. So I'm going to go ahead and erase that because we are going to call our vertical 0 degrees. So that guy goes away. Now you will notice that this guy has the same form of our x of t times our amplitude cosine of omega t plus phi. Again, if you are just watching this video online, this can also be written sine. We use cosine, just defining where our 0 is all that is. If you're in my class, don't worry about that. We have it all set up how we want to. With that, we have theta t is equal to a theta cosine omega t plus phi. So we want to know what this theta t is, and we need the amplitude. Well, our amplitude, our maximum angle is 10 degrees. I can write this as degrees or radians in this case. Anything in here has to be in radians. Outside, we can leave as degrees. It just means our answer is going to come out in degrees. So that will work either way for us. Times the cosine of our omega, so pi times 0.7 plus phi. Okay, this phi thing here. In our problem, we have been told that at time 0, we are vertical. So time 0, our pendulum looks like this. This is time equals 0. And what we've been told in the past, well, in setting up this equation, is we've been told that this set of equations is assuming that at time equals 0, we have a pendulum that is fully pulled out in the positive direction. We're assuming that at time 0, we're right here. And if we're not right there, we need to use this phi to correct for it. This is where we could also switch between cosine and sine. We're going to use this system instead. But basically, if we track our angle versus time, we are saying that we're starting right here, and the angle is going between 10 degrees and negative 10 degrees over time. And what's happening is after certain amounts of time, we're getting to our different places. So if we are starting at our maximum pullout, we're starting at this positive 10 degrees. At this point, we have a phi equal to 0. If we are starting at a position in the center and we are going to the left, we are at a phi equal to pi over 2 radians. If we are all the way to the left, we're all the way in our negative direction. We're starting at a phi equals pi radians. And if we're starting in the center but going in the positive direction, we are starting at a phi equals 3 pi over 2 radians. Or if we've already got a certain number, we can have multiples of these, or we can be in between these if I tell you that we're in between these at some angle. That becomes a little bit more difficult, but normally I will give you one of these options. Now, in the problem as I originally wrote it, I don't tell you whether we're going to the left or the right. I am going to assume that at time equals 0, we are going to the left. So time equals 0, we're going to the left, which means that phi is going to be pi over 2 for all of these problems. Okay, now that we finished that little segue, we're back to just a plug and chug problem. So pi over 2. So we've got theta at the given time is going to be 10 degrees times cosine of pi times 0.7 plus pi over 2. So with this is because this is radians per second, this is seconds, and this is radians. So radians, seconds cancel, and this is already in radians. So this guy comes out to be a theta at 0.7 seconds of, where do I have my number there? Negative 8.09 degrees. My guess position is incorrect. We've actually been going this way, and it makes sense. So we said that all the way to the left and all the way across is 1 second. And I have gone 0.7 seconds from here. So from here to here and back would be 1 second. And I am less than 1 second. I'm at 0.7 seconds. So at 0.7 seconds, I haven't made it all the way back. I'm hopefully going to see a positive rotation because we're half a second when we make it here. We're rotating back for the second half a second. But I'm still on the negative side. So we have negative 8.09 degrees. Now I could have gone and I could have said 10 degrees, and I want that in radians, so I have 360 degrees is 2 pi radians. But since this is out of the parenthesis, what I would be doing here in order to change this negative 8.9 degrees, I would be saying, okay, well, 2 pi radians divided by 360 degrees. And that actually gives me a value of negative 0.141 radians. But in this case, it's going to end up in exactly the same number. We have actually already accounted for that in our calculation. So we have that angle of 8.09 degrees at 0.7 seconds. First step done. Now omega. Well, omega is going to work exactly the same as our theta did, except we use our rotational piece. So omega at time t is going to be equal to negative a theta times omega pendulum times the sine, instead of cosine, of omega pendulum times time plus our phi. We know every single one of these values, so I have negative a theta is 10 degrees times omega p, and my omega p is pi radians per second times the sine of pi radians per second times my 0.7 seconds plus my pi over 2, which is my phi offset, and there we are. And that value is going to come out to a total of 18.47 degrees per second, or in this case, it doesn't really make sense to give values in degrees per second, so we do want to change this 10 degrees to radians. And this comes out to a rotational rate of 0.322 radians per second. And this is going to be 0.322 radians per second. And you know what, we might as well say that this is negative 0.141 radians while we're at it. We'll include everything, just in case it's needed. Okay, and the last step is exactly the same. We have an alpha at a given time. We have negative a theta times omega p now squared times the cosine once again of omega p times t plus phi. Rinse and repeat. With this is going to be negative. A theta was 10 degrees. I can change that to, we'll go ahead and include the conversion. So 360 degrees is 2 pi radians times omega p, which is pi radians per second, that whole thing squared, times the cosine of pi radians per second times our time of 0.7 seconds plus pi over 2 radians. And that is going to come out to a total value of 79.8 degrees per second squared, or 1.394 radians per second squared. Okay. Perfect. So that is my radial movement of everything at this time. Let's go ahead and switch up, and let's say that I want to know how fast this guy is swinging left to right. I want my X movement at this time. Sorry, some technical issues there. Coming back with that, what we have going on is we now have to figure out our position, velocity, and acceleration in the X direction at this 0.7 seconds. We have the rotational aspects done. So just to rehearse here, what we had is we had our pendulum, which started here It went 0.5 seconds and it swung to this outer position, and now it has started to swing back, but it hasn't made it back to the original position. It's currently at a negative angle. It is at a positive rotation rates because it's coming back in, and it is accelerating as it goes down. We've got the only force on it is this mass, which is going to be pushing it down. It's going to be pushing it in the direction it's going, so it is a positive acceleration. And we're all set to go there. So with this, before we go too much further, I'm going to go ahead and draw this up. So currently we have our mass acting way out here, and we know that at this time we are at an angle of 8.09 degrees. It's negative because it's this way. We have a velocity that is going in the positive direction, and we have an acceleration. I'm going to draw it slightly below it. So this is my acceleration total. This is my velocity total. Now I know how to solve for those two things. I know that my velocity total is just going to be equal to r times my omega, which again, make sure we're using our omega at 0.7 seconds. We don't want omega pendulum, that's talking about something else entirely. So we have my radius, which is somewhere here, 0.994 meters times my omega times my 0.322 radians per second. And that is going to give me a velocity in meters per second. So that gives me a value of 0.32 meters per second. However, that is in the tangential direction, that is along this rotation, it is not completely in the x. And in the same way, I can say that my acceleration total, or tangential, is going to be r times my alpha at 0.7. So that is going to be 0.994 meters times my total value of alpha 1.394 radians per second squared, and that is going to give me a tangential acceleration of 1.385 meters per second squared. Now this is not what we asked for. What we were asked for is we were asked for what is that x position at 0.7. We were asked for what is this velocity in the x at 0.7. And we were asked for what is this acceleration in the x at 0.7 seconds. I haven't been putting the seconds on. So what we need to do is we need to just go into trig. We have an angle. We know this is 90 degrees. We can figure out what our x is. So in this case, our x at our, we can make this pen work. Yeah, our x at our 0.7 seconds is going to be equal to our total length. So this is our 0.994 meters times, in this case, it looks like we have a sine of our angle, which is 8.09 degrees. We now need to make sure our calculator is in degrees if we use this, or we can say this is the sine of 0.141 radians. And I probably should have the negatives in here because our x should end up being negative. So this guy comes out to a total x of negative 0.140 meters. So negative 0.140 meters is the distance we are away from the center there. Same exact idea. We have our velocity in the x at 0.7 seconds is going to be equal to our total velocity, which was 0.32 meters per second. And in this case, when we pull these guys over, we want the x portion, and our angle is going to end up being right here. This is that 8.09 degrees. This is that 8.09 degrees. So it's going to be cosine of negative 8.09 degrees. Again, be careful with this because this is using our calculator in degrees. If we wanted to use it in radians, we would have 0.141. And that value gives me a velocity of 0.317 meters per second, positive because we're going to the right there. So everything is matching up. 0.317 meters per second. So I actually should these negatives, we should really just be keeping track of our angles here. But anyways, we have the 0.317 meters per second. And then we have our acceleration in the x at 0.7 is going to be our total acceleration, 1.385 meters per second squared times the cosine of 8.09 degrees. And that is going to come out to a total value of 1.372 meters per second squared. 372 meters per second squared. Okay. With this, we do have another option that we can use to solve this, and that is assuming that we have a very small angle, really 10 degrees or under. Maybe you could extend to 15. I think 15 degrees is something like 2% error. But we can also approximate these pieces in order to save a couple steps as a oscillation in the x. So long as we don't have some big sweeping pendulums, as long as you have a small angle, we can go through and we can solve this in a different way. And that way is basically saying that our x at any time t is going to be equal to our maximum a in the x times our cosine of omega t, so this is omega pendulum t, plus phi. And I am fine for small angles if you always just jump to this guy. Now this a in the x, we first need to calculate. So this is our maximum angle. So a in the x is going to be equal to, when we're using our 10 degrees, it is going to be our radius. So our length here, which was 0.994 meters, and I want the portion of that that is in the x, so that is going to be the sine of 10 degrees. Again, this is in degrees, not radians, so make sure your calculator is appropriately set. And that is going to give me a value of 0.173 meters. And with this, what I can do is I can just go ahead and approximate that my x and my t is going to be 0.173 meters times the cosine of omega p, which we have as pi. I'm not going to write everything out just for space and time here, times my time, 0.7 seconds, plus my pi over 2, which was my offset. And that comes out perfectly to negative 0.140 meters. Same exact piece. And using that same logic, my velocity in the x at time t is going to be equal to negative ax times omega p times the sine of omega p times my time plus my offset. Again, all I've done is I've replaced a theta with ax, and I've replaced omega with my velocity in the x. And this is going to come out to negative 0.173 times pi times the sine of pi times 0.7 plus pi over 2. And that comes out to a value of 0.319 meters per second. So when we didn't use the approximation, we got a value here of negative 0.31. No, this isn't negative. What am I doing? Positive 0.317 meters per second. And when I did it here, I got 0.319. This is really just assuming that the cosine of a very small angle is approximately 1, and that's where that small amount of air comes out. However, it's quick, it's easier, we can work with it. You may use this approximation if you would like. And in the same way, my acceleration in the x at any time, I'm just switching my alpha for acceleration in the x at a time. It's going to be negative instead of my a theta. I'm using ax, omega p times these. That is not sine. That should be cosine of omega p times t plus phi. That is going to be negative 0.173 times, this omega p should be squared, my apologies, times pi squared times the cosine of pi times 0.7 plus pi over 2. And that is going to give me a value of, sorry about that. I've got my notes sitting on the keyboard. 1.378 meters per second squared. 1.372 becomes 1.378. Again, we're well within that area. As long as we've got a small angle for our total oscillation, you may use this set of equations instead of the equations with the thetas. So that is a way to make that a little bit easier for us. Okay, we're not quite done. The last thing we are asked to do is we need to resolve the entire problem. Okay, maybe not the entire problem. We need to resolve the problem as if this length of string does have a mass. And we are told what the mass is. I will look that up in a second. I just need to finish erasing. We are now told that that piece has a mass of 1/2 kilogram. So that total length has a mass of 1/2 kilogram, and I want to figure out what my length nu is. So if this piece has some mass attached to it, We're saying that no matter what the length is, the mass is going to be 0.5 kilogram. What is my total, what is my overall piece? So this means that I can no longer use my equation that I used earlier, which was saying that omega p was equal to the square root of G over L. Yep, G over L. Instead, I need to change that equation to be my full proper version, which is the square root of my mass times gravity times my length. I'm going to put a little star next to this because that's not the length you think it is, divided by I. Okay? Because that length is the length to the center of mass of my overall piece. So in order to find that, what I need is I need to figure out my distance to my center of mass. So my distance to my center of mass is going to be the sum of all of my masses times all of the positions of masses divided by the sum of the individual masses. It's the average center of mass of the different pieces. So my different pieces, I have 2 kilograms acting at a distance of L. And I have 0.5 kilogram acting at a distance, well, the rod, the center of mass of a linear object, if we got even mass, the average position, the center of mass is going to be the center of that rod. So this is L over 2. That whole thing divided by the total mass, which is going to be 2 plus 0.5 kilograms. So I get my center of mass along this line is going to be equal to, in fact, I should probably call this, instead of X center of mass, we'll call this L center of mass, because it's where's the center of mass of this entire piece in this direction, because depending on where we send it, unless it's perfectly horizontal, it's not actually in the X. But that comes out to a value of 0.9 times the length of this rod. So just using L as a variable there. The other thing we need is we need this inertia. So our inertia is going to be our total inertia, which is going to be the inertia of the point plus the inertia of the rod. In this case, the rod is rotating around the end. So our inertia total, inertia for a point is going to be m times the radius to that point squared. And the inertia for a rod rotating around the end is 1/3 mass times the length of that rod squared. So filling things in here, we have the mass of 2 kilograms times the radius to here, which is L, plus 1/3. The mass of the overall rod is 1/2 kilogram times our L, which is going to be which is just L, yeah, times L squared. And that whole thing simplifies out to a value of 2.16 repeated times L. Okay, so we're trying to solve for this L. We have two variables that we have in terms of this L. So this is LCM with my new little terminology there. And I know what that omega p is supposed to be. So I'm going to start erasing things and replacing them with values. So this omega p is pi radians per second. That's right there. My mass is my total mass, so that is going to be equal to 2.5 kilograms. I'm going to have to erase the whole line at once. My mass is going to be 2.5 kilograms. My gravity is 9.81 meters per second squared. And my length center of mass is 0.9 L. And then my I is, that I'm dividing by, is 2.16 repeated. Oh, and this should be L squared. L squared. Otherwise, the L's would cancel. And I can go through and I can plug all of this into a calculator and solve for the L. So I'm going to take the pi, I'm going to square it. I'm going to multiply by the 2.16 L squared. I'm going to divide both sides by L, so I've got all of that. The L gets rid of here. This L squared, which I've now moved over here, becomes just L. Divide by whatever this number is, multiply by that L, and I get my final value. And that tells me that this length now actually has to get longer. I need a total length of 1.03 meters for my pendulum in order to make my grandfather clock move in such a way that my period, this is not period, that's time, that my period is 2 seconds. So with that, with this change, my omega hasn't changed, so none of these values have changed here to here. However, my radius has changed, so these three values are all going to change a little bit at that point. And that's just, instead of being multiplied by 0.994, it's going to be multiplied by 1.03 for the length that everything's acting at. But that is trivial, hopefully, at this point. But yeah, that is our example pendulum problem. Hopefully that was helpful. Take care.